Thank you, Giovanni, for the introduction. And first, it's a great honor to be invited and have the opportunity to present in this beautiful workshop. My name is Jilei Chen. I come from Institute for Quantum Science and Engineering in Southern University of Science and Technology. Today, the title of my talk is Long Decay Length of Magnon-polarons in bismuth iron oxide, lanthanum, strontium, manganese oxide heterostructures. So first is the outline. First is the introduction, and then I will present the sample information and the experimental results of magnon-polarons. And then is the theoretical model, and in the end is the summary and acknowledgements. So first, please let me briefly introduce the background of this study. So we studied the propagating spin waves. Spin waves can propagate in ferromagnetic materials, and also antiferromagnetic materials. So they need the line spins. When the spins start to precess, they can couple to their neighbors and form the spin waves. Spin wave can transport in magnetic materials without the motion of electrons. So it is free of Joule heating and beneficial for building low power consumption spintronic devices. In addition, compared to microwave at the same frequency, spin wave has the wavelength 4 to 5 orders of magnitude smaller. So it has the intrinsic advantage for making nanoscale devices. The major challenge for utilizing spin waves in large-scale applications is that spin waves have a relatively small decay length compared to other information carriers. We know that phonons can propagate in solids, in liquids, or in air with a very long decay length. So surface acoustic phonons can propagate in piezoelectric substrate excited by the interdigital transducers. And it has a lot of applications such as the surface acoustic wave sensors, oscillators, and filters. The coupling between magnon and phonon is now a hot topic in the study of hybrid magnonics. So it describes the coupling between spin excitations and elastic waves via magnetoelastic coupling. People realized the magnetoelastic waves in a ferromagnetic material and piezoelectric material-based heterostructures. And also, in the similar system, people could use the magneto-rotation coupling to control the non-reciprocity of surface acoustic waves. So in this study, we investigate the magnon-polarons, which is the hybridized magnon-phonon modes in BFO RSMO heterostructures. So here is our sample structure. We have on top the 20 nanometer thick BFO, and underneath is the RSMO 80 nanometers, and the NGO is the substrate. BFO is a multiferric material which possesses both the antiferromagnetic property and also the piezoelectric property. And RSMO here is a pure ferromagnet. Here we show the TM image of the BFO RSMO heterostructure, which we see the crystallization of this structure is quite nice. And here we show the main experimental results by the angle resolved spin wave spectroscopy. We change the angle of the external magnetic field and sweep the frequency. And in this spectra, we could see two prominent modes. One we named mode X, and the other we named mode Y. So we attribute these two modes as the pure magnon mode for mode Y and magnon-polaron mode for mode X. And we will come to this spectrum later. So first, I will show the magnetic damping characterization of this sample. So BFO is an antiferromagnetic material, so it has the intrinsic resonance at sub-terahertz regime. We cannot detect it by the FMR characterization. So the FMR signal mainly comes from the RSMO thin film. The damping is calculated to be 1.2 times 10 to the minus 3, which is much smaller than other metallic ferromagnets, such as permalloy or cobalt boron. And the oxide heterostructure and FMR characterization is provided by Professor Chen Nan's group at Tsinghua University. And then I will briefly introduce the measurement technique. We use the vector network analyzer based all electrical measurements method to study this heterostructure. Here we have the VNA connected to the coplanar waveguides or nanostrip-line antennas where the microwave cable and microwave probes. And underneath the antenna, we have the patent BFO aerosol heterostructure. In the experiment, we can rotate the external magnetic field to have the angle-dependent results. So here we show an SEM image of the nanostrip-line antenna. Here, this line is the antenna, and we can see the width of the antenna is around 270 nanometer, and we can vary the distance between two antennas to have the different propagation distance. And underneath the antenna, we have the BFO aerosol heterostructure. In the experiment, we rotate the the external field away from the 110 crystalline orientation of BFO aerosol heterostructure. Here we show the wave vector distribution of the nanostrip-line antenna, which we can see that for the strip line, it can excite a broadband K vector. We first show the reflection spectrum from the angle-resolved spin wave spectroscopy. For reflection spectra, we only need one antenna for both excitation and detection. And we fix the external field at 100 min Tesla and rotate the field with respect to the K vector. And here we show the S22 reflection results. In this spectrum, we mainly see two modes. One mode is here, in this shape, we name it mode A. And the other weak mode here, we slightly see the weak mode here, mode B here. For mode A, it has the highest frequency around 90 degrees, but for mode B, it has the different angular dependence than mode A. So for further investigating the origin of mode A and mode B, we perform the different measurements by changing the angle between the crystalline orientation and the strip-line antenna. So when in this scenario, we have the antenna in this here, and the wave vector is perpendicular to the antenna. So we have the wave vector K parallel to the 110 crystalline orientation, and we have this spectrum. When we rotate the strip line by 30 degrees, and the K is also rotated by 30 degrees, we could see that the spectra changes, which we see the mode A shifts by 30 degrees, but mode B stays in its previous position. When we further changing the angle to 60 degrees, we could see the mode A shifts by 60 degrees, but mode B is still in its previous position. So we see that mode A is sensitive to the wave vector direction. So it exhibits the angle dependence determined by the Damon-Ashbach spin wave mode to the back volume mode spin wave mode transition, relying on the wave vector direction. But for mode B, it is not sensitive to the direction of K vector. So, this mode B may relate to the crystalline orientation here, which may come from the in-plane uniaxial anisotropy given by the crystallization. For further investigate this in-plane uniaxial anisotropy, we perform the NV magnetometry measurements. So we perform two measurements in parallel. One is the single RSMO thin film, and in this row, and the other row, we perform the BFO RSMO heterostructures. So for the results of RSMO, we see that there is the periodical domain stripes in the sample with the up-down domain, and the period of this domain stripe is around 200 nanometers. And we could see that the domain stripes orientation is not fixed, and it's random, and we could also use a small external field to rotate the domain stripes. The spin dynamics and its current control manner of the domain stripes in the aerosol can be found in our previous publications. So when we move to another sample, BFO aerosol heterostructure, we see that the domain stripes follows the orientation of 110 crystalline orientation of RSMO. So the orientation of the domain stripes are fixed, and we cannot use a small field to rotate it. So it seems that there is some pinning effect from the BFO. So the results of the NVA measurements on samples with and without BFO suggest that the uniaxial anisotropy is associated with the BFO aerosol interface. And the NVA magnetometry is provided by Professor Martinsky's group at the University of Basel. And then we show the transmission spectra as to one. So for transmission spectra, we need two antennas, one as the excitation part, and the other is the detection part. So here we also fix the external field at 100 min Tesla and rotate the field. So here we show the experimental results of the S21 spectrum. And we mainly see two modes as we described before. But here we can see that this mode Y is covered by the shape of mode A from the reflection spectra, which means that this mode Y is a pure magnon mode, follows the transition from Dayman-Ashbach type to backward volume mode type. And at 90 degree, it's as the Dayman-Ashbach type spin wave, and we can draw a line plot here to get the delta F here to investigate the group velocity of mode Y. But mode X is prominent at around 50 degree and 130 degree, and it doesn't follow the trend of the mode Y. To further investigate the decay length of these two modes, we perform different measurements with varying the distance between two antennas and from 2 micrometer to 20 micrometer. So for the 2 micrometer device, we could see both mode Y and mode X very clearly, but when we move to 20 micrometer device, we could see the mode X is still there, but mode Y nearly vanishes. So it means that the decay length of these two modes are different. And we could estimate the group velocity of mode Y by using this equation, by extracting the delta F and 1 over D for linear fitting. And we get the velocity around 0.8 kilometers per second, which is very close to the pure magnon propagating mode in aerosol thin film. To further investigate the group velocity of mode X here, we perform another experiment, the time-resolved BRS measurements. So this image is taken by the BRS setup, and we fix the condition of mode X by fixing the external field at 100 mean Tesla, and the angle theta equals 48 degree. So in this image, this bright line is the nanostrip line, and underneath the nanostrip line, we have the BF or aerosol heterostructure. In the measurement, we focus on 2 points. P1 here is very close to the antenna, and P2 there is 5 micrometers away from P1. By comparing the time difference when the signal arrives at P1 and P2, we could get the velocity of mode X. Because mode X has a resonance frequency at around 7.5 gigahertz, so we inject a microwave pulse with 7.5 gigahertz into the antenna. This shows time-dependent results. And here we could see at the falling edge, as the rising edge here, and when we see a zoom-in spectrum, and we could see that signal first arrive at P1 point, and after some time, it reaches the P2 point. We could see also the falling edge. It shows that there is also a time difference. By extracting this time difference, and we know that the average group velocity of mode X is about 2.5 kilometers per second, which is much larger than spin wave propagating velocity in magnetic thin films. But this value is very close to the phonon, surface acoustic phonon velocity in piezoelectric materials. So we see that this mode could be related to the phonon mode. We also see a weak mode here. We have a very large delta T prime, and this mode has a velocity of 0.4 kilometers per second. So we think that this mode could be related to the pure magnon mode. So there are two contributions for mode X. One is the pure magnon mode, and the other is the phonon-related mode. The time result BRS measurement is provided by Professor Dirk Grunler's group at EPFL. And so then we come to the theoretical modeling, and we model the coupling between the magnons in ferromagnetic thin film coupled with the surface acoustic phonons via the magnetoelastic coupling. So the dynamics of the magnetoelastic coupling can be seen in this, can be described in this equation. In this equation, those 4 terms determines the magnon dynamics, and these 2 terms determines the magnetoelastic coupling, and this term determines the phonon dynamics. And FCC and F parallel here are the parameters which is described by the magnetic properties. And here, H here is the autoplane component of the driving microwave field, and F here is the amplitude of mechanical force density given by the magnetoelastic coupling. And the theoretical support is from Dr. K. Yamamoto and Professor Merkava's group at RIKEN. And then by solving that equation, we have two components. The one component is from the pure magnon mode in this form, and magnon-phonon hybridized mode in this form. And chi k here is can be described in this equation. In this equation, we see that there is a B effective, means the effective magnetoelastic coupling. We take the magnetoelastic coupling of 2 times 10 to the 5th rule per cubic meter and get the simulation results. Here, the first row shows the experimental results, and the second row shows the simulation results with different propagating distance. So we see that the simulation results mostly reproduce the experimental observations with both mode Y and mode X, and also the distance-dependent behaviors. So here, mode Y comes from the pure magnon mode in the simulation, and here, and mode X comes from the magnon-phonon hybridized mode. And furthermore, we could describe the dispersion of the hybrid magnon-phonon modes. Here it shows the dispersion relation. This term determines the magnetoelastic coupling. So it is dependent on the theta. Theta here is the angle between the external field and the wave vector. When theta equals 0 or 90 degrees, this term goes to 0. So if we see the plotted dispersion of magnon and phonon, and at the crossing point, there is no coupling. But when the theta is close to 45 degrees, we see that at the crossing point between magnon and phonon, it opens an anti-crossing gap. It means that these two modes are coupled. Furthermore, I want to introduce another experiment by replacing the nanostrip line by coplanar waveguides for further investigating why the mode X has the property of phonon-like behavior. So the CPW have the discrete k-vector distribution, and we see 3 peaks, K1, K2, and K3. When we see the transmission spectrum from the magnetic field dependent spectrum, we could see that here, the tilted one, this mode is the magnon mode, and we see 3 horizontal modes here, K1, K2, and K3. We attribute these 3 modes to the phonon modes, surface acoustic phonon modes. And here we fix the angle of 54 degrees, which is close to the condition of mode X. And by extracting the frequency of these 3 modes, we could draw a linear fitting of the phonon dispersion, and it yields the phonon velocity around 2.5 kilometers per second, which is very close to the value we get from the time-resolved BRS measurements. And when we zoom in to this region where the magnon mode crosses with the K3 phonon modes, we could see that by changing the rescale the color plot, we see that the kind of anti-crossing behavior between these 2 modes. But the anti-crossing is not very permanent because the magnon-phonon coupling strength is not large. And note that by calculation, the crossing point between phonon and magnon is at around 20 rad per micrometer. But our CPW could only provide the K3 mode at around 16 rad per micrometer. So what we measured is this green circle here. This is not exactly at the crossing point. So this mode may exhibit the phonon-like behavior because it's at the phonon branch. So it may have the phonon velocity and the phonon decay length, but it still has the magnon information because it's very close to it's approaching the coupling between the magnon and phonon. And here we draw the decay length of the 2 modes what we observed. For mode Y, decays very fast, and the decay length of mode Y is several micrometer. So, but for mode X, it decays very slow, and because there are 2 contributions for mode X, so we use this function to fix the decay length of mode X. Here, Cm and Cmp are the prefactors of the magnon mode and pure magnon mode and magnon-polaron mode. So lambda m and lambda mp here is the decay length of the magnon mode and the magnon-polaron mode. And fitted data yields the ultra-long decay length for the hybridized magnon-phonon mode to be 1 millimeter. But here, the lambda m here for the pure magnon decay length is around 5 micrometer. It's very small. So in conclusion, that we observed the long magnon-polaron decay length up to 1 millimeter at room temperature, and decay length of the magnon-polarons is more than 2 orders of magnitude than the pure magnons in RSMO. So the long decay length mode has the high group velocity around 2.5 kilometers per second, and the numerical calculations suggest that the magnetoelastic coupling hybridized the phonons in BFO and magnons in RSMO to form the magnon-polarons. So in the end, I want to acknowledge all the support and help from our co-authors and collaborators. And thank you so much for your attention. Thank you.